Signage and Wayfinding Design, a complete guide to creating environmental graphic design systems by Calori and David Vanden-Eynden. Chapter 6, The Hardware System. Sign hardware is the physical embodiment of signage, the environmental objects that display the sign information as conveyed via the sign graphics. The hardware system of a sign program is all the physical stuff you can actually touch or bump into. It's the tangible, three-dimensional, 3D, component of a sign program. The hardware system is also the vocabulary of shapes, structures, materials, finishes, mounting, and lighting, as well as the methods the EG designer uses to unify all these elements into a family of sign objects. See Figure 6.1. It is the three-dimensional, sculptural aspect of signage that distinguishes it from other forms of graphic design, an aspect that is more grounded in industrial and architectural design than graphic design. And its intrinsic three-dimensionality is what makes signage such an exciting design challenge. Many people think of signs as basically flat objects that display graphics, which they certainly can be, but as this chapter will show, a sign program's hardware system can be far more visually rich and exciting than a series of flat panels. In our office, we approach the design of a sign program's hardware system by asking a question. Since signage is inherently three-dimensional, how can we exploit that third dimension? This chapter examines the three-dimensional elements the EG designer manipulates in designing the hardware system of a signage program. It also provides an overview of basic materials, finishes, coatings, and lighting techniques that the EG designer fashions into physical sign objects. While the focus of this chapter is on fundamental concepts of the 3D attributes of signage, keep in mind that aspects of the sign hardware system are affected by the ADA and local codes, as with Chapter 5, the graphic system. This chapter touches only on some of those aspects, and it is not intended to be an exhaustive guide to, nor should be considered technical or legal advice on ADA conformance. See Chapters 4 and 5 for sources that provide ADA information, including the 2010 SAD document itself. Shape. Shape or form is probably the most obvious expression of a sign program's hardware system. The shapes used in a signage program give the program its visual unity and distinctiveness in three-dimensional form. Shapes are virtually limitless for the sign hardware system, and basic shapes can be combined and synthesized into even more distinctive shapes. This section looks at the vocabularies of basic sign shapes the EG designer can manipulate in hardware system design. Basic sign shapes based on mounting. Signs do not magically float in space. They must be mounted on or into something else, and what they are mounted to is a major determinant of the intrinsic form a given sign will take. Basically, signs are mounted on horizontal surfaces, such as floors or ceilings, from above or below, or on vertical surfaces, such as walls, from the back or side. This leads to the following four basic types of mounting. Freestanding or ground-mounted, in which the bottom of the sign is fixed to a horizontal mounting surface, such as a floor. See Figure 6.2. Suspended or ceiling hung. in which the top of the sign is fixed to a horizontal mounting surface, such as a ceiling. See Figure 6.3. Projected or flag mounted, in which the side of the sign is fixed perpendicular to a vertical mounting surface, such as a wall. See Figure 6.4. Flush or flat wall mounted, in which the back of a sign is fixed parallel to a vertical mounting surface, such as a wall. See Figure 6.5. The mounting or support structure for each of these types of mounting can be either hidden or expressed, leading to the following overall sign forms listed below and shown in Figure 6.6. Note that all of these types of sign mounting can occur at various heights, and that the ADA and local codes can affect those heights as well as other sign dimensions, as touched on in Chapter 5, the graphic system, and later in this chapter. Freestanding sign forms. Pylon or monolith, in which the entire sign body rises from the ground or floor. Lollipop, or sign on a stick, in which a sign panel on a single post rises from the ground or floor. Multiple posted, in which a sign panel on 2 or more posts rise from the ground or floor. Suspended sign forms. Suspended monolith, in which the entire sign body hangs from a ceiling or underhang. Suspended pendant, in which a sign panel on a single post hangs from a ceiling or underhang. Suspended multiple posted, in which a sign panel on 2 or more posts hangs from a ceiling or underhang. Projecting sign forms. Projecting monolith, in which the entire sign body projects from a wall or other vertical surface. Projecting lollipop, in which a sign panel on a single post projects from a wall or other vertical surface. Projecting multiple posted, in which a sign panel on 2 or more posts projects from a wall or other vertical surface. Flush-mounted sign forms. Wall plaque, in which the back of the sign is attached to a wall or other vertical surface, such as soffit or transom. Monolithic sign forms typically have hidden internal support structures, and wall plaques typically don't require expressed or visible mounting structures. The support structures are expressed, however, in the other sign forms just outlined. All of these sign forms, except relatively thin, flush-mounted ones, can be viewed in the round, providing opportunities for expression of the three-dimensional details, as well as providing faces for graphics on more than one side. All non-flush mounted sign forms can have a minimum of 2 sides for graphics, if graphics on 2 or more sides are appropriate and useful. Given the basic sign forms dictated by mounting factors, sign shapes can be generated based on geometry in elevation, plan, and sectional views, as shown in Figures 6.7 and 6.8. Elevation views depict the vertical surfaces of an object, front, sides, profiles, and back. Plan views depict the lateral footprint or perimeter of an object as viewed from the top. Sectional views expose the internal parts of an object, depicting slices cut through an object either lengthwise, longitudinal, or across, transverse, just as a carrot can be cut along its length or across it with the resulting slices exposing the carrot's structure differently with each direction of cut. The key views of sign shapes are elevation and plan, and they are examined in the following sections of this chapter. Vocabulary of basic sign shapes based on geometry in front elevation. An unlimited number of sign shapes, as viewed straight on in front elevation, can be generated from elements of the most basic geometric forms, the circle, square, and triangle. Hence, sign shapes in front elevation can be composed of curved, rectilinear, or angled elements, or combinations of these elements. Keep in mind that these shapes can be used for a sign panel on posts or can be used monolithically. Also, keep in mind that graphics are typically most efficiently fitted onto sign shapes that are overall rectilinear in front elevation. See Figure 6.9 for a basic vocabulary of front elevation shapes. These shapes can also be layered over each other to create different plane levels in front elevation, as shown in Figure 6.10. Vocabulary of basic sign shapes based on geometry in plan. The geometry of the top horizontal view of a sign body or sign panel, although generally more subtly expressed than the front elevation shape, can also provide a limitless number of plan shapes. As with front elevation shapes, plan shapes are composed of curved, rectilinear, and angled elements, as well as combinations of them. Keep in mind that plan shapes can be used for a sign panel on posts, for the posts themselves, and for monolithic sign bodies. See Figure 6.11 shows a basic vocabulary of plan shapes, and Figures 6.12a and 6.12b show the sign program with sign panels curved in plan. Also, keep in mind that some plan shapes, or variations thereof, can be rotated 90 degrees to the vertical and be used for the side elevations or profiles of signs. And to further compound shape generation possibilities, different plan shapes can be combined with different front elevation shapes, as shown in Figure 6.7, in which a wedge-shaped plan view is combined with a trapezoidal front view to create a distinctive sculptural form. A sign combining different plan and elevation shapes is shown in Figure 6.13. Connotations of form. While 3D sign shape and form do not literally communicate information in a denotative way as sign graphics do, the 3D aspect of signage has powerful stylistic connotations. Three-dimensional sign forms and the ways the ch designer synthesizes them into sign hardware objects have stylistic connotations in the same way the shapes of typographic letter forms do. The key, then, to designing a sign program's hardware system is to determine the appropriate 3D formal qualities of the project at hand. As an example of some of the formal aspects the ch designer mediates in a sign program's hardware system design, consider the myriad styles of that common everyday object we call a chair. Does the chair have a high or low seating height? Is it on four legs, a pedestal, or is it cantilevered? Is it mobile or stationary? Is it all one material, such as wood, or a combination of materials, such as steel and leather? Is it upholstered? Is it simple or complex? Is it traditional or contemporary? Similar stylistic questions come into play when designing a sign program's hardware system. It is beyond the scope of this book to delve into a lengthy examination of the connotations of 3D form, as it is a very complex subject, but its importance to highlight a few very basic pointers on signage hardware system form. Some front elevation sign shapes are inherently traditional or contemporary. For example, tombstones and horizontal oval shapes have more traditional connotations, whereas more basic shapes, such as squares and circles, have more contemporary connotations. See Figure 6.14. Sign objects are often a synthesis of many formal elements, particularly those signs with exposed fasteners or exposed structures such as posts, and each element has its own formal connotations. How these elements fit with and transition to one another is a key to the stylistic appearance of the sign object. Generally, the simpler and sleeker the sign objects, the more contemporary the appearance of the hardware system. Conversely, the more complex and ornate the sign objects, the more traditional the appearance of the hardware system. See Figure 6.15. The stylistic characteristics of the graphic system affect the stylistic characteristics of the hardware system, and generally speaking, the two should mesh. For example, a crisp, contemporary graphic system is better suited to a contemporary hardware system. Of course, there are some projects in which juxtaposing contemporary graphics with traditional hardware is entirely appropriate, even if difficult to pull off. Just as the appearance of the sign graphic system can be quiet and elegant or bold and flashy, so can the appearance of the hardware system. The key is determining which stylistic approach is more appropriate to a given project. For example, clean, simple, almost utilitarian hardware forms may be appropriate for a subway system signage, but not for a grand hotel signage. See Figures 6.16 and 6.17. At our office, we discuss whether a sign program's hardware system should fade away or stand out from the project environment, which has some correlation to the concepts of harmony and imposition discussed in Chapter 1, What is Environmental Graphic Design? Unity of form. It's relatively easy to develop shape or form for a single sign or type of sign, but signage programs are typically composed of several types of signs, which can range from small wall plaques to large freestanding and suspended units and everything in between. In other words, the ch6 designer must design a whole family of signs for a given project, and this family must be unified in appearance to enhance the sign program's cohesiveness and effectiveness. And just as a human family is composed of individuals, each of whom usually shares some visual similarities that identify them as a related family unit, so too, a well-designed sign program is composed of different sign types that share common visual features that identify them as related to each other. You can see examples of projects with unity of form within sign families in the gallery section at the end of this book. A sign program's graphic system contributes to two-dimensional unity, and a program's hardware system contributes to its three-dimensional unity, primarily expressed by a shape and form, and supported by materials, colors, and finishes. Maintaining unity of 3D form across a broad range of sign mounting conditions and sizes is one of the great design challenges in signage program development, one that really gets the creative juices going. In contrast to architectural design, which typically embraces the design of a singular object, albeit a highly complex one, a building design of a signage program's hardware system is more akin to industrial design, in which several different individual objects are often designed as part of a larger line of related products, such as cookware or furniture ensembles. It's difficult to pin down how an EG designer creates unity of form within a sign family's hardware system, but it typically relies on consistent use of a common or similar 3D detail, or a combination of details throughout all the sign types, regardless of size or mounting condition. In a program, see figures 6.18a, B, and C. Simple examples of common details and detail combinations include designing all the sign panels in a program to be curved, or designing all the sign panels in a program to be curved and then overlaid on partially exposed flat background panels. Commonalities in mounting structures, such as ground-mounted posts and ceiling suspension hangers, are details that can also lend formal unity to a sign program's hardware system. See the gallery section for examples of formal details that unify sign programs. EG designers don't need to be slavish in adhering to a common 3D detail or details, but they do need to employ some sort of consistency to visually relate all of the hardware elements of a sign program to each other. Continuing with the curved panel example just given, within a specific sign program, sign panels that are curved in plan may be more appropriate for vertically formatted signs, while panels that are curved in side elevation may be more appropriate for horizontally formatted signs. The key common detail feature is the curved panels, not whether they're bowing out on the horizontal or vertical axis. The EG designer can use sketches, drawings, simple study models, and 3D computer modeling applications to develop 3D formal unity among all the sign units in the program. It's always useful to look at the entire sign family together and at one scale to see how the units formally relate to one another in the program's range of mounting conditions as well as in the program's range of sizes. Sign mounting considerations. As stated earlier in this chapter, how signs are mounted is a key determinant of a sign's form, and this section of the chapter explores the factors the EG designer must consider for sign mounting. Overhead and eye-level mounting zones. A sign's location, viewing distance, and hierarchy help determine mounting heights and methods. There are two basic zones for placement of sign information, and therefore for mounting the sign panels that carry that information, an overhead zone and an eye level zone. Generally, for interior environments, signs that convey primary and sometimes secondary information are mounted in the overhead zone. Signs that convey detailed and/or lowered hierarchy information are mounted at eye level. The reason for this rule of thumb makes sense. Important primary sign information needs to be located high enough so that it's not obstructed by people, vehicles, plants, or other objects in the environment. Less important sign information doesn't need to be, and in fact shouldn't be, so prominently placed, and detailed sign information has to be placed at eye level for close study. See Figure 6.19. For example, in an airport, primary directional signs and identification signs, such as gate identification numbers, are typically mounted overhead, whereas signs conveying less important information, such as office identification or detailed information, such as an airport orientation map, are placed at eye level. See Figure 6.20. Of course, many environments, such as museums and hotels, are often more subdued and low-key than those of airports, and in these more subdued environments, overhead signs may be completely inappropriate. There are also situations where it's useful to repeat the same information in both the overhead and eye level zones. A good example of this is a signage program for a retail store in a mall, where an overhead primary identification sign is installed for viewing across the expanse of the mall, and a secondary identification sign is placed at eye level to enable people walking along the storefronts and underneath the primary sign to read the same information. The zone for displaying eye level sign information is roughly between 3 feet and 6 feet 8 inches above the finished floor AFF. The zone for displaying overhead information is anywhere above 6 feet 8 inches AFF. Keep in mind that if detailed sign information is displayed below 3 feet, many people would have to stoop to read it. And if it's displayed above 6 feet 8 inches, many people would have to crane their necks to read it. Also keep in mind that overhead information is often displayed on tall, ground-mounted signs, not only on suspended or projecting signs. In the midst of this book's discussion of the overhead and eye level zones, it's important to remember that the ADA has specific provisions related to sign mounting heights. For example, the SAD requires a specific mounting zone for baselines of tactile/raised characters on identification signs for permanent room, which is within the eye level zone defined here. The SAD also has a table that specifies character cap height based on 3 specific visual character mounting height zones, as well as lateral proximity distances. This table spans both the overhead and eye level zones defined here, and does not permit baselines of interior visual characters to be mounted as low as the lower limit of the eye level zone discussed in this section. Additionally, the ADA also has a general requirement for a minimum overhead vertical clearance, which affects all interior and exterior overhead signs on pedestrian circulation paths, such as ceiling suspended, post-mounted, and projecting overhead signs. Keep in mind that these are but a few examples of how the ADA relates to overhead and eye-level zones discussed here. As stated in Chapter 4 and 5, EG designers need to thoroughly familiarize themselves with the ADA/SAD. Refer to those chapters for ADA/SAD information sources. The concept of overhead and eye-level zones is somewhat different for exterior signage programs. Generally, for pedestrian-oriented exterior signage, these zones are the same as previously discussed. For example, detailed pedestrian information such as neighborhood maps or bus schedules should be placed in the eye-level zone for comfortable reading, and directional information should be placed in overhead zone so it's above most obstructions in the exterior environment. Wear and vandalism are also considerations for exterior pedestrian signage. The lower sign panels are placed, the more prone they are to being hit by moving objects, covered with graffiti and stickers, or degraded by other kinds of wear and tampering. Although the eye-level zone is applicable to exterior pedestrian signage, it has little applicability to vehicular-oriented signage. Beyond drive-up windows at banks and fast food purveyors, where drivers are not moving and can study detailed information such as a menu, vehicular sign information, by necessity, must be succinct for rapid assimilation by drivers moving at speeds up to 70 plus miles per hour. Because of the speed factor, the information on the vast majority of exterior vehicular signs is not and cannot be studied in great detail as can eye-level interior and exterior pedestrian signs. The Manual on Uniform Traffic Control Devices, MUTCD, as discussed in Chapter 5, the graphic system, is a valuable reference when designing vehicular signs. Generally speaking, when it comes to designing vehicular signage, the slower the speed, the more detailed and lower the sign information can be placed. Moreover, the level of detail of vehicular sign information rarely approaches that which is feasible for pedestrian signage. That is, although vehicular sign information can range from less to more detailed, it can rarely be as detailed as pedestrian signage information. For example, on high-speed roadways such as freeways, primary information must be limited to as few words or lines of text as possible to communicate the message. Many, in fact, comprise only of 1 or 2 words. At lower speeds, drivers can absorb more information, such as when they approach an intersection with a stop sign or traffic light, and slow down long enough to read directional information for several destinations. Vehicular signage can be literally overhead and that drivers pass underneath the sign information. For example, signs mounted on overpasses above the garage entrances and on freestanding sign support structures spanning the roadway. While these pull through or pass under signs are fairly common in vehicular signage, more common are pass-by vehicular signs, which are mounted adjacent to the roadway and often require far less complex support structures than freestanding pass-under signs. Pass-by signs are typically mounted lower than pass-under signs, but still need to be held high enough to minimize obstruction by vehicles, trees, and other objects in the roadway environment. Another important factor is that the human eye has a limited range or angle of vision. Unlike the Google Street View cameras, we do not have 360-degree horizontal vision, and we don't typically rotate our eyes and our heads and necks unless absolutely necessary, such as when backing out of a parking space. Accordingly, signs should be mounted within normal/natural lines of vision when people are looking straight ahead. Horizontally, the angle of vision extends 20 to 30 degrees, 40 to 60 degrees total, from the vertical center line of the eyes when looking straight ahead. Figure 6.21 depicts a sign mounted perpendicular to the line of sight within a 60-degree field of vision. Note, however, that other diagrams may indicate a more dynamic horizontal vision field for people moving in cars based on proximity to the sign. Vertically, the angle of vision extends 10 to 15 degrees up and down from the horizontal center line of the eye. Figure 6.22 shows a 10-degree angle up from the center line. It doesn't show a downward angle because other objects tend to obscure sign information placed below the horizontal center line, unless the viewer is within relatively close range of the sign. As noted above, people typically will not rotate their heads to read sign information beyond their horizontal angle of vision. Likewise, they generally will not crane their necks to read signs in the overhead zone. Figure 6.22 illustrates how sign mounted in the overhead zone should be primarily for distance reading. It also illustrates how the top height of a sign can increase with viewing distance, as well as how the size of a sign, along with its graphics, should increase with viewing distance. This information about sign mounting zones and viewing angles and distances can be useful to e.g. designers, but it is fungible and therefore should not be considered a mutable fact. Sign viewing is a dynamic process with many variables, particularly regarding whether the viewer is moving forward on foot or on wheels. As with many other aspects of e.g. design, such as typographic size, the designer should conduct some degree of testing, formal or informal, to determine sign mounting positions suitable for the conditions of the project at hand. Three-dimensional computer modeling applications can be helpful to informally test sign mounting positions. And, as always, the e.g. designer must keep in mind conformance with local codes and the ADA signage provisions, which, in many cases, are more stringent than the general mounting zone dimensions discussed above. Architectural and site factors affecting mounting. As clearly stated throughout this book, signage programs exist within an environmental context, be it interior, exterior, or both, and the e.g. designer needs to consider the physical characteristics of the environment within which the signs are to be mounted. Ceiling clearances, wall and corridor widths, obstructions such as columns or trees, and other elements will affect sign mounting decisions. For example, a given building may have ceilings that are too low for ceiling suspended signs to provide the minimum ADA clearance, given the sign information content at the minimum visual character cap heights per the SAD table. In such cases, ceiling suspended signs may not be a design option, so the e.g. designer must consider other types of mounting, which will in turn affect the formal qualities of the sign hardware system. Another architectural site factor in whether the environment provides adequate opportunities to mount signs on existing structures such as walls, columns, and ceilings for interior signs, or light poles and overpasses for exterior signs. In situations where there are no appropriately located existing structures for sign mounting, such as in the middle of a shopping mall's atrium or an open urban plaza, freestanding signs will be necessary, which naturally has formal consequences for the hardware system. It's also possible that the EG designer may find that freestanding mounting is completely appropriate for certain sign types, even when existing structures are available for sign mounting. In an urban signage example, the EG designer may determine that freestanding signs will provide clear sightlines and encourage less visual competition than sign panels mounted on existing structures such as light poles. Sign mounting must be structurally stable. Therefore, it must be coordinated with architectural or site conditions. Whether the sign program is for an existing environment or new construction, in new construction, the EG designer can coordinate sign mounting with the project architect, structural engineers, and or sign fabricator. In existing environments, the EG designer can coordinate sign mounting with the sign fabricator and or structural engineer if an architect isn't involved. Exterior ground-mounted signs require footings or foundations, which are concrete legs or pads that penetrate deep into the soil to anchor the sign. The above-ground sign structure can be directly buried into the fresh concrete footers or can be attached at a later time by anchor bolts to the structure laid with the footings. In either case, the ground must be dug to lay the footings, which means that below-grade utility lines may be breached during the digging. To avoid interfering with local services such as water, electric, data, or sewer, the sign fabricator should call for a markout of utility lines in the installation locale. Indeed, in many locales, digging without a utilities markout is against the law. As you'll learn later in this chapter, there are myriad ways to join sign parts together and to join signs to their mounting surfaces. But as stated in Chapter 2, the design process, EG designers are not trained or licensed to practical structural engineering or architecture, and should therefore specify that all engineering of sign structures and attachments be performed by professionals in those fields or by the sign fabricator. Sign size considerations. Many of the same factors that must be considered regarding sign mounting must also be considered regarding sign size. Certainly, the relationship of viewing angle, viewing distance, and mounting height is a key determinant of the size of any given sign type, as are architectural and site factors, such as low ceiling or limited wall space. And as stated in chapters 4 and 5, sign hierarchy and the quantity of message content are two other key size determinants for any given sign type. So important are they, in fact, that it bears repeating that it is imperative to design for the worst case, longest message or set of messages programmed for each sign type. For vehicular signage, road speed and the number of lanes affecting the amount of time and the distance that drivers have to react to a sign. These factors in turn affect the letter height of a sign message and the total area of the sign panel that displays the message. As shown in Figure 6.23, the information in Figure 6.23 is a starting point only, and as with sign mounting, some degree of testing is necessary to determine the letter heights and panel sizes most suitable for the project at hand. Recall from chapters 4 and 5 that local codes may dictate message content and the cap heights of messages for certain interior signs, typically those with life safety messages. Although not all codes mandate a specific size for the actual sign panels on which such messages appear, some do, so it's always important to check the local codes applicable to the project at hand and see if certain panel sizes are mandated. And even when panel sizes for such signs aren't specifically mandated in a code, the message content and graphic sizes dictated by the code will play a role in determining panel sizes. This is also the case with the ADA. Although the SAD doesn't require specific sign panel sizes, its requirements for attributes of sign graphics, such as sizes, positions, spacing, and others, affect the panel sizes on which the graphics are displayed. Also note that the SAD section on protruding objects, which is separate from the SAD's signage section, places dimensional limits on 3D objects, including signs in pedestrian circulation paths. Generally, these ADA limits include depth of objects protruding from walls, overhang of single post-mounted objects, vertical clearances of double post-mounted objects, and vertical clearance of overhead objects, most within specific vertical or horizontal ranges. Both interior and exterior sign dimensions can be affected by the requirement of the SAD's protruding objects section, and the EG designer is advised to become familiar with all the specifics of its requirements. Sources for ADA/SAD requirements are provided in chapters 4 and 5. Chapter 4, the Information Content System, explains how local sign ordinances may restrict the size of exterior signs, usually expressed in terms of square footage. Other sign ordinance restrictions may include other aspects of the hardware system for exterior signs, such as height, form, or shape, materials, illumination, and other factors. Overall size. Thus far, this section has focused on the size of sign panels and part of a sign that displays messages as opposed to the overall size of a sign, including its mounting structures. In the case of flush, wall-mounted signs where the back of the sign panel is mounted directly to a wall, there is no visible ancillary structure to support the sign panel, so the overall size of this kind of sign is the sign panel itself. In the case of freestanding, suspended, and projecting signs, however, there is some sort of support structure for the sign panel, and this structure contributes to the overall size of the sign. As noted earlier in this chapter, the support structure may be exposed, as in the single vertical post of a lollipop sign, or may be hidden, as in a monolithic pylon. This discussion but the overall size of a sign is germane to local sign ordinances, as they may restrict two aspects of size: actual height from the ground to the top of the sign, height restriction, and the square footage of the sign, area restriction. Refer back to Chapter 4, the Information Content System, for more on local exterior sign ordinances. Depth. Another important sign hardware size consideration is depth. We can't forget that signs, even flush-mounted wall plaques, are three-dimensional objects, and that depth is that added third dimension. Depth of a sign can range from negligible, essentially two-dimensional or planar, to deeper than its length or width. Factors that contribute to determining depth include the depth required of mounting structures to adequately secure the sign, informational requirements. Signs with messages on one or two sides can be relatively thin, but signs that have information on three or more sides need to be deeper to provide an adequate message area on each sign face. ADA/SAD limitations on depth of objects, including signs, protruding or projecting from walls into circulation paths. As stated previously in this section, the SAD also places other dimensional limits on signs on circulation paths, the visual effect sought by the EG designer. Proportion and scale. Proportion and scale are related to size in the sign hardware system. The rule of thumb for proportion is to trust your gut. That is, if a freestanding sign looks too thin depth-wise to stand up, it probably won't unless it has major foundational support. Conversely, excess depth can make signs appear too bulky. Accordingly, to achieve three-dimensional proportional harmony, it's important at the very least to study the front and side view of all the sign types in a sign program. Quick study models and the 3D computer rendering programs can be even more helpful for visualizing and refining sign program forms and proportions. Always consult with a sign fabricator or engineer if you have any questions about structural matters. The EG designer can also manipulate the scale of the sign hardware system in relation to the program's environment. The scale of the various sign types can be just right for their surroundings, or the scale of a certain or all the sign types in a program can be enlarged to create a bigger, more dramatic visual impact. In certain environments, smaller scaled signs may be appropriate to create a sense of subdued elegance, but they should never be so small that they cannot be easily read at the intended viewing distance or that they do not conform to any ADA or local code requirements for typographic or panel sizes. A final word about size in the sign hardware system. The fewer sign sizes there are in a program, the more visually unified the program will be. Keep in mind that a sign of a given size can display variable quantities of information content, from a little to a lot, although never so much as to cause information overload, depending on how the various kinds of sign messages are laid out in the graphic system. Sign lighting overview. Just as lighting adds interest and drama to stage productions, lighting can add interest and drama as well as visibility to signage. Lighting components are physical objects, making sign illumination part of the sign hardware system. Basically, there are three options for lighting signs: external, internal, or non-illumination. This section presents a basic overview of sign lighting techniques in relation to each of these sign illumination options. Decisions on whether to light and how to light some or all the sign types in a program depend on many factors, among them whether a sign is an interior or exterior environment, ambient light levels within the sign program's environment, a sign's hierarchical rank, primary, secondary, tertiary, within the program, cost considerations, local sign ordinances, the desired visual effect, and others. In addition, new technologies and products for lighting signs are always being developed, so the EG designer may want to engage a lighting consultant, electrical engineer, or sign fabricator for more technical information on sign illumination. Electrical power is required for both external and internal illumination. Typically, electrical power from the grid must be brought to the sign location, which is a cost factor that requires coordination between the EG designer and the project architect or electrical engineer, as well as between the sign fabricator and other construction trades. Ongoing electrical consumption is another cost factor. Sign illumination may be on around the clock or be controlled with an automatic timer to save energy. The latter is the case in particular for exterior signs or interior signs in high daylight environments. Maintenance is also a consideration, as most illuminated signs must be checked periodically to replace burned out lamps and to ensure that other electrical components are in good condition. Due to these costs and maintenance factors, lower hierarchy signs within a program, such as room identification plaques in a hotel, are rarely illuminated. It's also important to remember that local sign ordinances may place limitations on the illumination of exterior signs, such as dark sky requirements to reduce glare and light pollution from a variety of lighting sources. In signage programs for new construction, the earlier the EG designer can identify the locations of illuminated signs, the easier it will be for the project's engineers to coordinate sending power to those locations without change orders or ripping out finished surfaces to lay electrical conduits. Even if it's still undecided as to whether a given sign type may be illuminated, it's wise to have power run to the appropriate sign locations so that the power is there when or if needed. Of course, the EG designer should be judicious and not have power run to hundreds of sign locations where it's unlikely to ever be needed. The previous paragraphs apply to traditional sign lighting and the electrical delivery methods. That said, white light emitting diode LED lighting has revolutionized sign illumination and, to a certain extent, electrical power delivery to signs. LED lamps have longer life, consume less power, and have fewer hazmat disposal consequences than the former workhorse of the sign industry, fluorescent lamps. In some cases, the power consumption of LEDs can be low enough that the sign power source can be solar, which does not require wired connection to the electric grid or consume power from it. Solar power does require collection and storage devices and is a rapidly developing technology, so it can be useful for the EG designer to consult with a sign fabricator or sign lighting manufacturer who has knowledge of current solar energy technology and components. Whether signs are grid-wired or solar-powered, or externally or internally illuminated, at the minimum, the EG designer should be aware of the items noted below. Keep in mind that sign fabricators, lighting consultants, and lighting manufacturers can be useful sources of technical assistance on sign illumination. Externally and internally illuminated signs must be fabricated so that they are evenly illuminated with no so-called hot or cold spots. All electrical components must be Underwriters Laboratory, UL, approved and in conformance with any applicable safety or energy codes. All electrical engineering for a sign program should be performed by other parties with the proper credentials, such as an electrical engineer or a sign fabricator. External illumination. The term external illumination refers to lighting that is outside of a sign but specifically dedicated to and aimed at the sign for purposes of illuminating it. See Figure 6.24. This definition does not include ambient lighting, which is lighting dedicated to other purposes in the sign environment, such as general room or street lighting. External lighting reflects off a sign surface and is achieved with floodlights or spotlights directed onto either the entire sign face or just the sign graphics. External illumination is more commonly used for signs in exterior environments than interior environments, although it can make for very dramatic effects in interior settings. External light sources include LED, fluorescent, halogen, mercury, or sodium vapor, incandescent, and other kinds of lamps. Although all these sources emit what is generally considered white light, the color temperature of the light varies with the source, and the color temperature of the light source can tinge the color of the sign itself. For example, sodium vapor lighting has an orangey cast, and mercury vapor has a bluish cast. Even white LEDs and common tubular fluorescent lamps are available in various color temperatures, ranging from cool to warm. The fixtures housing external lighting sources can be mounted below or above the sign and can vary from sleek and minimalist to highly noticeable, so the look of the lamp fixtures must always be considered in external sign illumination as much as their position to reduce glare and light spillage. One external sign illumination technique that doesn't require electrical power is specifically engineered reflective vinyl films that capture, intensify, and reflect light back from car headlights. These retro-reflective vinyl films are available in white, black, and a limited range of bright colors. They can be used for reflective sign graphics, reflective sign backgrounds, or both. But a word of caution here. Never use reflective black film on reflective white film or vice versa, because both reflect white light, resulting in disappearing graphics. Retro-reflective vinyl films are manufactured in a variety of grades and are typically used for traffic control and roadway directional signs at sites where there is little or no ambient lighting at night. See Figure 6.25. Internal illumination. Internal illumination refers to light that is transmitted from within a sign. See Figures 6.26 through 6.32. It is commonly used for signs in both exterior and interior environments. As such, internally illuminated signs can take several forms, and most common being a rectangular sign box with a translucent plastic face on which the graphics and background are completely backlit, increasingly by white LED lamps, which are rapidly overtaking fluorescent lamps as the light source. This entirely backlit box form is typified in signs of big box stores, gas stations, and other commercial establishments. Some internally illuminated sign boxes have just the graphics backlit on opaque backgrounds, which is less commercial in appearance, while others have only the background backlit with opaque graphics. Typically, the light source is an internally illuminated sign is completely hidden. although sometimes the glowing light source itself is the sign, as in those made of exposed neon or other luminous tubing. Some internally illuminated signs aren't even rectangular boxes. Instead, they're individually fabricated letters that can be lit in 3 ways, with light coming through the face of each letter, with light coming through the face and returns, sides of each letter, or with light spilling out around the returns of an opaque letter in a halo or silhouette effect. Another form of internal illumination is edge lighting, where a source light is aligned on the edge of a transparent glass or plastic sheet and is conducted through the transparent sheet to illuminate graphics etched or sandblasted into it. Translucent vinyl is also often used for graphics on edge-lit signs. There are many light sources for internal sign illumination, with new forms and technologies being developed and refined on a regular basis. White LEDs have largely overtaken the tubular fluorescent lamps, which were the workhorses used to backlight most sign boxes. Similarly, LEDs have largely replaced custom-bent neon-type lamps for backlighting individually fabricated letters. This LED sun lighting revolution, which continues to evolve, has allowed thinner sign boxes and smaller backlit letters, with the added benefits of energy saving and longer lamp life. Another benefit or detriment, depending on your viewpoint, is that certain LED lamps can sequentially change color from white to any number of colors. E.g., designers should be aware of poor LED sign lighting applications, which include hotspots on backlit signs and any application that reveals the point sources of the individual LED lamps unless the goal is to emulate strings of holiday lights. Typically, internally illuminated signs must be thicker than other types of signs to accommodate lamps and their mounts. The space required between the lamps and the sign face, plus wiring and any other electrical components, providing access to the interior of sign boxes for servicing lamps and electrical equipment, is also an important consideration when designing internally illuminated signs. The E.g. designer should take care to specify that all internally illuminated signs be fabricated to prevent leakage of light at seams and joints, with adequate venting to dissipate any heat that can build up within the sign. Additionally, the E.g. designer should specify that all illumination is to be even, with no hot or cold spots. Non-illumination. Non-illumination of signs is a perfectly viable option for signs in exterior or interior environments with high enough ambient light levels, whether from artificial or natural sources, for signs to be seen and read without dedicated sign lighting. Entire sign programs have been developed with no illumination at all for many environments and function perfectly well. Non-illumination also makes sense if the site doesn't operate at night or if an overly commercial look is not desired. Non-illumination is obviously the least expensive option, requiring no electrical installation, no ongoing on-grid energy consumption costs, and no costs for solar energy collection and storage devices. Sign materials overview. Sign materials are just that. Raw materials such as pallets of aluminum sheets or steel I-beams. It's the E.g. designer's creative mind and the sign fabricator's skills that give the materials form and life as three-dimensional sign objects. And that is one of the truly magical aspects of E.g. design. Materials are the essence of a sign program's hardware system. They are the very stuff from which signs are fabricated. As such, they have a significant bearing on the visual appearance of the sign hardware system. The E.g. designer has a virtually endless range of materials from which to compose a sign program's hardware system, and fascinating new materials are introduced on a regular basis. An entire book could be written on sign materials, so by necessity, this section highlights only the basic materials that can be used in the sign hardware system. Some sign materials are used as purely structural components, either expressed or hidden, while others are used as exposed finished components, such as sign faces, plaques, and cladding over internal structures. And some sign materials, such as wood and aluminum, are used as both structural and finished components. Materials as your muse. The guideline here is, let the materials be your muse. Certain sign materials that are inherently attractive are rarely covered up with paints or other opaque coatings, although they may require a clear coating for protection. Other sign materials are covered up with opaque coatings because they need to be a specific color. They need to be protected from the elements, or they're inherently unattractive. Most materials can take a variety of finishes: smooth, rough, grained, and so on, that either come from the material's manufacturer or are added in the sign fabricator's shop. More on this later in the overview of sign coatings and finishes section. Each basic type of sign material has inherent qualities such as the transparency of glass, the flexibility of fabric, or the shininess of metal. And each of these qualities can and should be exploited by the EG designer. Plastics are perhaps the ultimate material chameleon, in that they can mimic glass, metals, or even wood and stone. Plastics also have inherent qualities that are valuable unto themselves, such as ease of formability, break resistance, and their relatively light weight. Several examples of the various sign materials available are shown in Figure 6.33. Unity of materials. Unity of materials is just as important to the visual coherence of a sign program's hardware system as unity of form. As with sign form, the point is to use a unified materials palette to create a family resemblance among all the various types of signs within the program. This doesn't mean that all the materials within the program's palette need to be used on each and every sign type, but that perhaps one or two materials are featured in all the sign types in the program. See the gallery section at the end of this book for examples of sign programs with unified materials. Materials and processes. Materials for exposed sign finish components are available in a variety of forms, most commonly in flat sheets, plates, or slabs of various thicknesses that can be processed in various ways, depending on the specific kind of material. All flat finish materials can be cut into various shapes or drilled with holes by various processes. Aside from cutting and drilling, workability diverges with the inherent physical properties of each basic material. For example, as shown in Figure 6.34, sheets of metal can be bent to an acute angle or rolled into a curve relatively easy. But stone can't be bent or rolled because it's brittle and will break. In another example, plastic is the only sign material that can be readily vacuum formed into a specific shape by heating the plastic sheet and drawing it down over the shape with a vacuum pump. After the plastic cools, it retains the shape. It is apparent from just these two examples that there are many workshop processes for even basic sign materials, and that new processes such as 3D printing, discussed in Chapter 5, are becoming available. So a comprehensive discussion of them is beyond the scope of this book. There is no doubt, however, that EG design is facilitated by a basic knowledge of the techniques by which various sign materials can be processed in a shop, and there are several sources for gaining that knowledge. The SEGD website provides a message board for its members, where both professional designers and industry fabricators and manufacturers Members share information about sign materials and fabrication processes, among other topics. Most SEGD industry members are willing to meet with EG designers to discuss materials and production techniques for a given project, and are often willing to conduct shop tours for EG designers, which can be very illuminating to both newcomers and seasoned professionals in the field. Additionally, SEGD industry members hold a trade exposition at the SEGD's annual conference, which is a wonderful source of information on materials and fabrication processes, including several that are cutting edge. EG designers can also access technical information at www.signweb.com, which is geared toward sign fabricators, or by attending the International Sign Association's annual expo, which showcases both cutting-edge and traditional sign materials and manufacturing processes. Materials for sign structural components, whether expressed or hidden, are available in a variety of forms. Wood structural components are typically solid and available in several cross-sectional shapes, such as square, rectangular, round, and sometimes more elaborate shapes, such as fluted columns or turned spindles. Metal structure components are typically hollow or open extrusions or forgings. Many of these shapes are used for general construction industry applications and are available in a variety of basic cross-section shapes, such as round, square, and rectangular tubing, as well as L-shaped angles, C-shaped channels, and the classic I-beam. There are also manufacturers of extruded aluminum support components with more varied sectional shapes geared specifically to signage applications. Size does matter. It's important to keep in mind that both finish and structural signage materials are manufactured in certain standard sizes, as this will have consequences for the appearance of a sign program's hardware system. Not only can material size be a design constraint, but so can the size of equipment for working, finishing, or applying graphics to the material. Size is generally less of a problem with the smaller sign types within a program, but it can become a major challenge when working with the larger sign types, where seams and joints can become a design factor. Seams and joints can generally be minimized or hidden on opaque or painted over materials such as metal, wood, and opaque plastics, but they cannot be hidden on fabrics or transparent materials such as glass or clear plastics. When faced with material or processing size constraints, the EG designer will often press the reveal technique into service, which is a neat design trick that actually exposes and plays up a seam or a joint. This can often look better than trying to hide a joint that can't be hidden successfully. From a green standpoint, size can come into play with smaller sign points cut from larger material stock. The goal in such cases is to size the signs cut from the larger stock in such a way as to minimize the amount of unused material that's left over. See Figure 6.35. Sign fabricators can provide guidance to EG designers on this consideration. Basic sign materials. While reading about the basic sign materials described in this section, keep in mind that there are many proprietary products with their own unique qualities and properties within these broad categories of sign materials. Additionally, there are many products that are composites of these materials, capitalizing on properties of each constituent material to create a new set of properties. For example, an aluminum plastic sandwich that's as flat as a solid sheet of aluminum of the same thickness, but with substantially reduced weight. And of course, new sign materials are constantly under development. Sources for information on materials and products used in signage include manufacturers and suppliers' catalogs, design and architecture magazines, and companies that provide compendia of manufacturers such as Sweets and the Thomas Register. Most of these sources, as well as others, can be found on the internet e.g. www.materialconnection.com, which is invaluable for conducting materials research. Also note that EG designers should always obtain samples of materials they're considering for use, and that most materials manufacturers are happy to provide samples to designers. Most EGD offices maintain a library of materials information, ranging from catalogs and swatch books to samples and mock-ups. A word about sustainable design and materials. It is beyond the scope of this book to examine the environmental factors relating to materials and processes for a sign program's hardware system, or for application of sign graphics. Suffice it to say that EG designers should always consider the environmental impact, from sourcing to manufacturing and processing to delivery, to disposal and recycling of the materials and processes they specify. Good, solid design that's not overly trendy and therefore not quickly dated also contributes to environmental sustainability. The SEGD Green Paper on Sustainability, available at the SEGD website, is a good source of information on green practices in EGD. Metals. Metals in both structural and sheet forms are among the most highly utilized sign materials. Additionally, certain metals can be melted and cast into complex forms, including hardware components such as sign bases and as medallions and plaques. All metals have good to excellent structural properties, although they all oxidize or corrode to a greater or lesser extent. Metals can take a range of surface finishes, from a mere polish to a coarse brushed grain. Metals can also be painted, although stainless steel, bronze, and brass are so attractive in their natural state, they rarely are. Typical metals used for signage include aluminum, used for sign faces, plaques, cladding, trim, and lightweight to medium weight structures, as well as for castings. Considered one of the white metals, aluminum is a lighter shade of gray than stainless steel. Other characteristics include good appearance, good durability, lightweight, and medium to high expense. Aluminum also typically benefits from clear or opaque protective coatings, although such coatings are not necessarily required. See Figure 6.36. Carbon steel. This metal is typically used for concealed medium weight to heavy weight sign structures, not for appearance. Other characteristics include high durability, heavy weight, and medium to high expense. Carbon steel also requires rust-inhibiting paints or coatings. Stainless steel. Stainless steel is typically used for sign faces, plaques, cladding, and trim. It's generally too expensive for structures. Another of the white metals, stainless steel is a darker shade of gray than aluminum. Other characteristics include excellent appearance, it's rarely painted, excellent durability, heavy weight and high expense, because it does not rust or rusts minimally, hence the name stainless. Protective coatings are not usually required. See Figure 6.37. Bronze, brass, and copper. These copper alloys, also called the yellow or red metals, are typically used for sign faces, plaques, trim, and castings. Like stainless steel, they're too expensive for structures. Other characteristics include excellent appearance, good to excellent durability, heavy weight, and high expense. These alloys also require a protective coating to maintain their metallic shine, although often they're intentionally oxidized to a rich brown or green patina before coating, or allowed to weather naturally without coating. See Figures 6.38 and 6.39. Plastics. Plastics have a number of unique properties that can be exploited for signage, such as transparency, formability, break resistance, and relatively low weight compared to other sign materials. As such, plastics are another commonly used sign material, although they're used primarily for exposed finished components, not structural components, and because certain plastics allow light to pass through them and their shatter resistance. They are almost always used for internally illuminated sign faces. Plastics and plastic resins are also moldable by various processes into an infinite variety of shapes, an invaluable feature in signage design and production. Plastic in sheet form are most commonly used in signage, although plastic resin liquids and pellets can also be cast into various sculptural forms. See Figure 6.40. The two primary sign plastics are acrylic and polycarbonate, commonly called polycarb, both of which have the glass-like properties of transparency and translucency, but unlike glass, they don't chip and shatter. In fact, polycarbonate is the clear, bulletproof material used to shield bank tellers and presidential limousines. There are some technical differences between acrylic and polycarbonate, but they are both used for sign faces, plaques, cladding, and trim, due to their capability to be transparent or translucent. They are widely used for the faces of internally illuminated sign boxes and letters. They're also widely used for vacuum-formed sign faces that have graphics in relief, as well as for clear protective lenses on signs such as directories and menu boards. See Figures 6.41 and 6.42. Acrylic sheet, in particular, is available in a fairly wide range of colors and textures, from completely transparent to completely opaque, and both acrylic and polycarbonate can be painted to a custom color. There are several manufacturers of acrylic and polycarbonate sheet, each with its own trade name and line of colors, texture, and other features. Grades with UV inhibitors should be used for exterior signage, as both acrylic and polycarb tend to yellow with exposure to the sun. Both feature a good appearance, medium to high durability, light to medium weight, and medium to high expense. Most plastics, including acrylics and polycarbonates, do not require any applied protective coatings, but they do tend to scratch more readily than other sign materials. Other plastics used in signage include styrenes, vinyls, phenolics, and photopolymers, all of which have their own unique properties. There are several manufacturers of signage materials, which typically come in sheet form, some of which are flexible, made from these types of plastics. Many are sold under trade names and use proprietary manufacturing techniques that result in unique products, such as expanded polyvinyl chloride (PVC) sheet that's half the weight of solid PVC sheet, but it's very strong for sign panel use. Other specialized plastics used for signage include metallicized or holographic films and sheets, photosensitive plastic sheets which yield tactile/raised and braille graphics when exposed to light and are chemically processed, and plastic resin sheets embedded with all kinds of decorative materials or with glass fibers for strength. The list of proprietary plastic products that can be used for signage is virtually unlimited, and new products are constantly being introduced. A word of warning though, some of these plastic products look downright cheap and tacky, whereas others are very attractive. Glass. Glass was invented centuries before plastics, and because of its inherent transparency, glass has long been used as a signage material, particularly as clear protective lenses on sign cabinets such as directories. Glass has also long been used for edge lighting applications and as the tubing that encases neon and other luminous gases used for signage. Glass sheets is used for sign panels, lenses, and plaques, typically in transparent form with the familiar slightly greenish tint. A completely colorless, low iron content glass sheet is also available, but at greater expense. Additionally, glass sheet is available in a wide variety of colors, levels of transparency, or opacity, and surface textures, typically from specialized art glass suppliers. Glass sheets is very hard and scratch resistant, but with a great enough impact it will shatter or chip. For this reason, glass is often tempered or laminated or both. Tempered glass sheet is treated after manufacture so that it will crumble into rectangular clumps rather than shatter into shards on impact. Tempered glass, however, cannot be cut, drilled, sandblasted, or otherwise mechanically processed without risk of breaking, so any tooling or incised graphic application processes should be performed before a glass sign is tempered. Laminated glass can be tempered or not, and consists of 2 or more sheets of glass that are permanently laminated together with a plastic inner layer that holds the glass fragments together if the laminated sheet is impacted. The lamination interlayer is quite strong. In fact, the most common application of laminated glass is in car windshields, which deform little even if riddled with cracks from an impact. Large freestanding glass signs can be self-supporting if made from several sheets of glass that are laminated together. Although laminated edges should be protected from the elements on exterior signs, also, many glass suppliers can provide graphics on the lamination interlayer as well as manipulate the interlayer's color, texture, and opacity. Ceramic frit, which is applied to a glass surface and baked to become integral with it, is a very durable graphic application technique for glass. See figures 6.43 through 6.47. Glass sign panels typically need a support structure, which is usually visible due to the transparency of glass. Supports can include a continuous frame that surrounds the sign perimeter or individual supports at strategic points. Although opaque glass panels can be supported by hidden structures, frameless glass signs should always have eased edges, which are very slightly beveled at a 45-degree angle to prevent chipping and ease the sharpness of 90-degree cuts. Other characteristics of glass include excellent appearance, good to excellent durability, heavy weight, and medium to high expense. It does not require protective coatings, but it must be cleaned periodically to maintain transparency. Wood. As sign materials, wood and wood products are less commonly used today than they were used a few decades ago, having been replaced by a great extent by new materials on the plastics front. Nevertheless, wooden products made from wood, such as particle board, are still used for some signage, including sign faces and plaques, as well as for lightweight structures. Wood products come in both structural and sheet forms, from cheap pine 2x4s and plywood to fancy lathe-turned posts and exotic solid hardwood or veneered panels. All wood products can be painted or clear-coated and can take a range of surface textures from smooth to highly textured. Typically, the more lowly and unattractive the wood product, such as medium density fiberboard, MDF, the more likely it is to be used simply as a substrate panel, to be covered up with paint and graphics. On the other hand, richly grained hardwood can be exploited for its attractive appearance in signage design, as it is in a fine furniture and cabinetry. In many cases, surfaces of lower quality wood products are laminated with a veneer, which is a thin layer of high quality wood, often with unusual graining. See figures 6.48 and 6.49. Other characteristics of wood products range from poor to excellent appearance, low to high durability, light to medium weight, and low to high expense. Wood products, particularly in exterior applications, must be protected with opaque paint or clear sealer. Fabrics. Fabric is a sign material that has the unique property of flexibility. Consequently, it is typically used for exterior signage application such as awnings, billboards, banners, and flags. In the case of awnings and billboards, the fabric is stretched over a rigid frame. Fabric banners and flags are freer to move with the wind, so they can lend animation and a festive quality to a site. See figure 6.50 and 6.51. Typical sign fabrics are made of natural fibers such as cotton or synthetic fibers and can be opaque, translucent, or open mesh. Certain sign fabrics are available under trade names in a fairly wide range of colors, including some metallics. Translucent vinyl-coated sign fabrics are commonly used for internally illuminated awnings and sign faces, and opaque vinyl-coated sign fabrics are used for billboards and other large outdoor signs. A reinforcement netting is often woven into these vinyl-coated fabrics, which can be visually objectionable when viewed at close range. Obviously, sign fabrics cannot be used structurally, and all fabric signs have limited lifespans. When necessary, they should be coated with UV inhibitors to reduce degradation from sun exposure. Most fabric signs have a good to excellent appearance and a low to medium durability. They are lightweight and their expense is low to medium. Keep in mind, however, that fabrication and installation of structures to hold fabric signs involve additional expense. Masonry. Masonry is a somewhat uncommon material for signage, but thanks to its inherent monumentality, it can be used to great effect. Masonry materials for signage include stone, brick, and precast concrete varieties that are typically used in architectural applications. Masonry can be used for sign faces and plaques, and masonry signs can be either solid and self-supporting or supported by an internal steel structure. Stone, the most prestigious of the masonry materials, includes marble, granite, slate, limestone, sandstone, and others, and many textural and color varieties of each of these types of stone are also available. Stone can be used for both exterior and interior signage, although many marble varieties are too soft for exterior use. Stone surface textures can vary from a mirror polish to a rough natural texture, depending on the type of stone used. Like glass, exposed edges of certain types of stone may require easing to reduce chipping and sharpness. Other characteristics of masonry sign materials are very good to excellent appearance, high quality durability, heavy weight, and high to very high expense. See figures 6.52 to 6.54. Adhesives and fasteners. Adhesives and fasteners are literally the glue and tape and nuts and bolts that hold signage hardware units together and signage hardware units to their mounting surfaces. Adhesives used for sign hardware are far more sophisticated than ordinary household glues and tapes, and include liquids, gels, and tapes that can establish extremely powerful bonds between surfaces of sign components without physically penetrating the components. In fact, some of the adhesives used in the sign industry come from the aircraft industry, where they're used to bond aircraft skins to airframes. Indeed, some adhesives are considered to create chemical welds. Adhesives are typically used to join finished sign materials to each other or to structural components, as well as to secure signs to mounting surfaces. Fasteners include nuts, bolts, screws, clips, and other devices typically made of metal that penetrate sign components to form strong mechanical connections within sign units and between sign units and mounting structures or surfaces. Mechanical connections are very strong and are usually necessary for securing sign structures together, for securing sign bodies to their structures, and in the case of heavier sign units, for securing sign units to mounting surfaces. Unlike adhesives, which form an effectively permanent bond, mechanical fasteners have the advantage of being removable, which allows access to the interior of sign units for servicing, such as to replace burned out lamps or to update directory listings. Fasteners are manufactured from a variety of metals, including stainless steel, galvanized steel, aluminum, brass, and chrome-plated brass. When attractiveness and corrosion resistance are considerations, stainless steel fasteners are often employed. But because fasteners often join dissimilar metals such as aluminum and stainless steel, they and the metals they join must be protected against corrosion that results from a weak galvanic or electrical reaction that occurs when dissimilar metals come in contact with one another. Many mechanical fasteners and connections are not terribly attractive in appearance, but often they can be concealed, sometimes with ease, sometimes with difficulty, depending on the application. But there are times when there's no choice but to leave the fasteners exposed to view. In such situations, the EG designer may choose to minimize the appearance of the exposed fasteners by hiding them in a reveal or painting them the same color as the sign panel. Alternatively, the designer may choose to accentuate the appearance of the exposed fasteners, thereby making them a design asset rather than a liability. Fortunately, there are several types of fasteners that are quite attractive and thereby suitable for exploitation as a design feature. Some designed objects, such as the Eiffel Tower, revel in their exposed mechanics. Others, such as the Statue of Liberty, also engineered by Gustave Eiffel, intentionally hide their nuts and bolts. The choice boils down to what is the appropriate aesthetic for the project at hand. Examples of signs and sign programs with purposefully exposed fasteners can be found throughout this book. Welding is another form of mechanical connection in which two pieces of the same metal are essentially melted together along a joint by heat or electricity. Welding forms very strong connections and is often used for connecting hidden structural components. Welding can also join together finished sign components when the raised bead formed by the welding process is ground smooth. Regarding sign mounting, lighter sign units such as wall plaques can be readily secured to mounting surfaces with just adhesives, typically double-sided foam tape, which is often used in conjunction with silicone gel adhesive. Adhesive mounting is often combined with mechanical fasteners, such as when a foam tape/silicone bond is augmented with mechanical fasteners for extra mounting support, a combination known as screw and glue, and mounting pins for individual cut or fabricated letters or for heavier sign plaques are often secured with adhesives or mechanical parts into pockets drilled into a wall. Large and/or heavy sign units often require connection into a building's underlying structural system, which can be inches or sometimes feet beyond a ceiling or wall surface. In cases where ease of changeability is a consideration, there are several methods and products, many proprietary for attaching signs together or to mounting surfaces, while discouraging tampering and allowing relatively easy changeability. These methods and products provide connections that make it possible to remove sign panels or other components. They range from magnetized sheeting to slide-in windows and lenses to hook and loop fasteners, commonly known as Velcro, a trademarked product, and more. In a sustainability note, fasteners are considered more environmentally friendly than adhesives for two primary reasons. First, fasteners don't release noxious solvents or fumes like many adhesives do. A second, fastener allows easier disassembly of materials for reuse or recycling when the signs have ended their useful life. Joining in sustainability efforts, manufacturers of adhesives used in the sign industry are developing more eco-friendly products, which is welcome since adhesives are useful in historical projects which often prohibit mechanical fastening to historical building materials. Electronic digital display units. Electronic digital displays, also called dynamic digital displays or variable message systems, draw the human eye like a flame draws a moth. These glowing, often animated devices are digitally controlled screens that display changeable and updatable sign messages, such as the Flight Information Display Systems, FIDS, at airports. Other applications of electronic digital displays include menu boards, hotel events, interactive building and campus directories, time and temperature displays, train departure/arrival information, scoreboards, stock tickers, marquees, and countless others. The EGD communication possibilities of electronic digital displays are endless, as is the need for changeable, updatable information. Chapter 1 has an overview of the relationship of digital communication devices to more traditional EGD media, particularly static signage and basic definitions of types of digital devices currently in use. These being digital signage, interactive kiosks, and mobile devices. Chapter 1 also distinguishes digital signage and interactive kiosks, which use electronic or dynamic digital display screens deployed in a permanent location to display pre-programmed information from mobile devices, which have portable screens that the phone or tablet owners carry with them to select any personalized information they want or need. That said, tablet devices are being increasingly deployed in fixed locations to display pre-programmed information, which may or may not be interactive. See Figure 6.55. This section of the chapter provides an overview of the electronic display units that are deployed in fixed positions for the display of dynamic or changeable information on digital signage and interactive kiosks. The electronic display units that are used on mobile devices are developed by the phone or tablet manufacturer and then selected by the buyer of the mobile unit. The EG designer and the mobile device's owner, for that matter, has little or no control over what display screen technology is used on mobile devices. There are situations, however, in which the EG designer may have some control over the display unit selected for deployed digital signage and interactive kiosk applications. One of these situations includes the fixed deployment of mobile tablets that deliver pre-programmed information such as hotel meeting room schedules or product information in a manner similar to digital signage or interactive kiosks. There are several hardware and software components used in the process of generating, delivering, and displaying changeable electronic information on digital signage and interactive kiosks. As discussed in Chapter 1, the process and components are complex and expensive, and often involve several areas of technical expertise beyond the e.g. designer's milieu. As stated previously, this book's focus is on static signage programs, but since digital devices are becoming more a part of an overall environmental communication or branding strategy, an overview of the actual deployed units and display digital information is in order. Since digital information technology is changing so rapidly, this overview is not intended to be an exhaustive treatise on how to become an expert in all aspects of that technology, but merely to familiarize e.g. designers with the basic types of display unit technology currently used in the deployed scenarios. Since these display units are the physical objects people most associate with deployed digital information displays, they are included in this chapter on the sign hardware system, but keep in mind that other physical components typically not visible to the sign user are also part of the digital information delivery system. Non-physical components such as software and content are also essential for digital information delivery. At the time of this writing, two of the most common digital display units are light-emitting diode (LED) matrices and liquid crystal display (LCD) screens. With LED and LCD devices, the sign, message, or image is displayed on the unit itself and can range from static words or images that update periodically to full motion video. Projection mapping is a different technology that can project spatially mapped images and video onto remote three-dimensional surfaces or objects, such as walls, building facades, bridges, and other large-scale environmental objects. LEDs are light-emitting diodes that generate their own light and have no need for supplemental lighting to be seen. LED matrices are orderly assemblages of the tiny LEDs into columns and rows, and can consist of a single color such as the familiar monochrome amber or red LED displays, or they can be combined into RGB groups to display a full color range. LED matrix modules can be seamlessly assembled into very large screens of more or less customary proportions. Think rock concert or sporting event screens, or into horizontal linear ribbons. Think Times Square zippers. The resolution of conventional LED matrices tend to be fairly coarse, but it's constantly improving. The rather large depth of conventional LED modules can be a design consideration. See figures 5.56 through 6.58. Organic LEDs, OLEDs, have a much finer resolution than conventional LED matrices and are much thinner and can even be flexible and transparent. Due to their relatively high expense, OLEDs are currently being adopted primarily for small-scale displays, such as on some mobile phones and tablets. It's likely only a matter of time before OLED technology becomes more cost-effective for use in large-scale deployed digital display units. LCD screen technology is too complex to describe without several paragraphs, and even then you'd scratch your head. Suffice to say, they provide full color and good resolution within limited screen proportions, also known as aspect ratios. Think the flat screen television or the computer monitor in your home or office. LCD screens do not produce their own light, so are backlit, originally by fluorescent lamps, but now primarily by white LED lamps, hence the misnomer LED screen, which is probably intentional because it sounds ultra high-tech, but actually just describes how the LCD screen is backlit, not how the screen images are generated. Large LCD screens are used as deployed digital display units. Small LCD screens are used for mobile phones and tablet displays. Like everything else in the digital realm, LCD screens are evolving rapidly with bigger sizes, higher resolution, smaller bezels, the enclosing frame surrounding the screen, and thinner depth profiles being developed every day. While LCD screens have fixed aspect ratios, screens can be ganged up into unlimited configurations to create video walls or towers. Smaller bezel sizes reduce the window pane effect of ganged LCD screens to create an almost seamless digital display surface in large-scale deployment. See Figure 6.59 through 6.61. When considering the use of LED and LCD display components for deployed digital devices, the EG designer should be aware of the following hardware system design considerations for these units: size and proportional limitations of active display area, bezel size, display unit depth, and dimensions of any other associated hardware components that may need to be located adjacent to the display unit. Resolution and viewing angle limitations, need for electrical and datacom feeds. Electrical is typically hardwired. Data can be delivered via hardwired or wireless technology. Venting, heating, cooling, and weather protectant constraints. Brightness of viewing environment, which is increasingly mitigated by sensors that automatically adjust screen brightness to change in ambient light conditions. In addition to the above, the use of mobile tablets in deployed situations has other considerations for the EG designer: securing the tablet from theft, need to recharge tablet batteries, prohibiting user selection of non-pre-programmed information, for example, using a deployed tablet to surf the internet or check the weather in Shanghai. Other considerations for dynamic display units are control and content, which are typically beyond the skill base of most EG designers, as discussed in Chapter 1. Electronic digital display units are basically empty canvases, waiting to be filled with text, image, and/or video content. How that content is delivered to the displayed device is the control component. What that content is composed of and how it's presented is the content component. All dynamic digital display units are computer controlled, with varying degrees of scale and sophistication. The display units can be tied into a larger computer or communications network maintained by the client, can be of their own dedicated network, or can be individually controlled, all via wired or wireless connections. The point is, each installation is different, hence requires information technology (IT) experts to create or tailor control software to each specific display application. Some basic applications, such as electronic menu boards, are available as packages that require relatively little technical support. Content for dynamic display devices can range from simple, generic text messages to sharp typeface and graphics rendition to full streaming video, depending on the display technology and resolution. Even non-video text and image content can be animated with flashes, crawls, dissolves, wipes, zooms, and other simple techniques. Although EG designers don't often have the opportunity to become involved in the actual production of content for deployed dynamic display devices, the appearance and quality of that content are concerns because more often than not, both are lacking. At our office, we always advise our clients to consider carefully the nature of the content that will be displayed, who will generate that content, how that content will be sequenced and presented, who will update and manage the content over time, and other similar concerns. Keep in mind that digital content nature, mix, sequencing, action, and other aspects may be limited by local codes or authorities, particularly in large public deployments where aesthetic, distraction, safety, and other factors are concerns. The best source for information about dynamic display units are their manufacturers, as they tend to have the most up-to-date technical information about their display products. Some display manufacturers can also provide control systems, including the computer hardware and software, engineered for their units and the client's need, along with the training for the end users on the client side. Some IT consultants and AV integrators draw from a number of sources to assemble completed turnkey systems for the delivery and display of digital information, which include cabinetry for the display units, content management, and sometimes development, all controlling systems and equipment, installation, and end-user training. Due to the diverse and developing skill set related to deployed digital information systems, the static signage industry has not been the leading force in this area, but that is evolving with knowledge, expansion, technological development, and client demand. To a certain extent, the same can be said for EG designers. As stated in Chapter 1, the digital information field is changing rapidly, and partnerships and shared knowledge can help clarify and harness this rapid change. Once again, it isn't the point of this book to go into deep technical details about digital information systems, so designers and sign fabricators can learn more and stay abreast of development by tapping the resources of the SEGD, the International Sign Association, the Digital Screen Media Association, the Digital Signage Federation, and digitalsignagetoday.com. Stock sign hardware systems. Back in the static signage realm, there are several manufacturers of proprietary stock sign hardware systems in several different styles, some quite attractive for both interior and exterior use. Each of these stock systems, typically patented, offers a unique hardware system, often with specialty interlocking and/or changeable parts. Most stock systems are kits of hardware parts that can be configured in many different ways by the EG designer. Manufacturers of stock systems also offer a range of techniques for applying graphics to their hardware systems, which also provides creative opportunities to the EG designer. See figures 6.62 and 6.63. Although this book is geared towards custom design sign programs, including the hardware system, we mention stock hardware systems because they can sometimes play a useful role in sign programs that are primarily custom designed. A strategy of adopting stylistically compatible stock systems or components of them can make a good sense for certain sign types within a custom design program. Such situations include when ease of changeability, maintenance, and cost saving are critical factors. Stock systems have both pros and cons. Pros include ease of changeability and maintenance. This feature is particularly useful for static building or mall directories that feature several strips listing tenant names, which change on an ongoing basis. Many stock directory manufacturers often convenient strip reorder services that provide new strips that match the originals in size, color, and material, as well as in typeface, type size, and type position. This ease of changeability is also useful for employee name and other signs requiring regular updating. Additionally, many stock manufacturers offer software and templates so that end users of their products can print their own new inserts in-house. Other stock sign components are also easily replaced. Design cost savings. Because the hardware system is already designed in a stocky system, EG designers don't need to spend as much time as they would on custom design of the hardware aspect of a sign program. Note, however, that even with stock systems, the EG designer still must spend time researching the various available systems, evaluating the selected one, and configuring and specifying it for the project at hand. Of course, the EG designer must also develop the graphic system for a stock hardware system, which is important to keep in mind because a unique graphic system can customize the appearance of a stock hardware system. Manufacturing cost savings. These should accrue due to the fact that sign fabricators don't have to completely reinvent the wheel when using stock systems. However, to make a finished sign, many stock systems still need to be worked by cutting, painting, and assembling, applying graphics, and so on, in the manufacturer's or fabricator's shop. Nevertheless, the manufacturing cost for a stock system can be lower than for a custom-designed, custom-built one. Cons of having stock hardware systems include the following. Stylistic limitations. Because each stock hardware system is pre-designed, each has its own three-dimensional appearance, which doesn't lend itself to much manipulation by the EG designer, thereby locking the designer into a given style that is undistinguishable from that of any other project using the same system. Size limitations. These tend to be more of a problem with exterior stock systems than interior ones, because exterior systems often are not large enough to carry typographic sizes adequate for good readability by drivers, unless they're used in lower speed environments, such as service drives and parking areas. Even interior stock systems may not be available in sizes or proportions that suit the necessary message content or viewing conditions. Quality. Some stock systems have materials that look downright cheap, and/or have parts that fit together badly. In this regard, be aware that the photos in stock system catalogs can be deceiving, so the EG designer should always obtain actual samples of any stock system under evaluation to assess their quality and suitability for the project at hand. Most stock systems are available to the trade, meaning that they can be purchased by custom sign fabricators for use in larger overall sign programs that are primarily custom. A few stock systems, however, are still available only directly from the system manufacturer, which makes them difficult for the EG designer to incorporate into a larger program involving custom fabrication, as this situation requires two different sources for the program signs: the stock system manufacturer and the custom sign fabricator. Sign materials and codes. From the preceding discussion of sign materials, it would seem an endless palette of materials is available for the EG designer to manipulate on a formal basis. It's important to know, however, that the use of certain sign materials may be prescribed by both local sign ordinances and building codes. For example, a local sign ordinance for a historical district may require that all exterior signs be made of painted carved wood, or at least have the appearance of being made of such materials, to maintain the district's historical quality. Sign ordinances for other districts may favor the use of fabric banners, or masonry signs, or metal signs accented with neon, or there may be no restrictions on sign materials. Sign ordinances also may prohibit certain materials, such as metal sign boxes with internally illuminated plastic faces or electronic digital display units. Building codes can also prescribe certain sign materials, usually for life safety reasons. These codes typically concern flammability and durability of sign materials, as well as the integrity of structural and electrical systems. Overview of sign coatings and finishes. Just as there is a wide array of materials used for a signage program's hardware system, there is a wide range of coatings and finishes that provide decorative or protective surface treatments for sign materials. As in the earlier section of this chapter on materials, this section provides an overview of basic coatings and finishes for basic sign materials. And, as with materials, samples and swatches of coatings and finishes under consideration should be obtained whenever possible. Finally, like materials, coatings in particular have characteristics that warrant consideration in sustainability strategies. The meaning of the term coating is fairly clear, is a dissimilar substance, such as paint, that's applied to the surface of another material, thereby creating a new final outer surface. The term finish, however, can be more confusing because it's often used to refer to two slightly different things. On one hand, it can refer to the gloss level of an applied coating, such as matte finish paint. On the other hand, it can refer to a surface texture created on a material, such as brushed finished aluminum. In both senses, the word finish refers to surface treatments, but the formal meaning involves a substance applied to the material, while the latter involves the material itself. To minimize this confusion, this chapter will use gloss level instead of finish when referring to coatings. Note that the SAD requires a non-glare finish or low gloss level on sign surfaces. Coatings. Coatings for sign hardware components include paints and clear coatings, powder coatings, porcelain enamel, patinas and oxide coatings, and vinyl or other plastic films. Each of these basic coating categories is described in more detail here. Paints and clear coatings. Paints and clear coatings, often referred to as liquid or organic coatings, are probably the most common and well-known coatings for signs. These coatings are typically applied as liquids and dry to a thin solid film. Extremely versatile paints and clear coatings can be applied to virtually any material on the planet and can easily conform to complex three-dimensional shapes. Not your ordinary roller-applied latex wall paint, exterior sign paints are specifically formulated to withstand the ravages of continuous exposure to the elements, sun, rain, ice, snow, and sand, just as automotive paints are. Manufacturers of sign paints offer a wide range of colors, including metallics and pearlescents, and gloss levels from high gloss to dead matte. Each sign paint manufacturer offers its own range of colors, and most sign paint systems can provide custom matching of colors from another color system, providing the EG designer with a virtually unlimited palette of colors from which to choose. See Figure 6.64. Sign paints typically require a primer or base coat that's applied directly to the sign material before application of the top coat, which contains the selected color. Sign paints are usually applied by spray gun to achieve a smooth, even surface, and are baked in a large oven after application to cure the paint, which dries and hardens it. In addition to opaque sign paints, there are also liquid clear coatings, which typically perform a protective function while allowing the base material to show through, just as clear polyurethane varnish protects a wood floor while allowing the beauty of the wood's grain to show. In signage, clear coats are commonly used to prevent the darkening and discoloring that oxidation causes on the yellow and red metals such as brass or copper. Aluminum is also often clear-coated to reduce oxidation, although it is not strictly required since oxidation doesn't substantially affect the appearance or strength of aluminum. In addition to their use on unpainted materials, clear coats are often applied over painted sign materials, just as they are on many of today's automotive body components. As well with opaque paints, clear coats are available in a wide range of gloss levels. For many years, sign paints and clear coatings were formulated with a relatively high level of harmful volatile organic compounds, VOCs, as solvents. Sustainability concerns have led many paint manufacturers to develop low or zero VOC coatings suitable for sign industry applications. Ongoing research and development continue to expand and improve these more eco-friendly choices. Most full-service sign fabricators have in-house equipment for applying conventional and low/no VOC paints and clear coats to signs. Powder coatings. Powder coatings, like paints, are dissimilar coatings applied over sign materials and are generally considered more durable than paint coatings. Also, like paints, powder coatings can easily conform to complex shapes, but unlike liquid paints, powder coatings are finely ground, electrically charged particles that are sprayed dried upon the sign material. The particles are held in place by an electrostatic charge until the coated material is heated in a curing oven to fuse the particles together into a uniform coating. Due to the relatively high heat involved in powder coat curing, it was originally used only on metals, but technological developments were making it increasingly possible to use powder coats on plastic and wood materials. Powder coating is a newer process than liquid coating, so it's not as widely used as other coatings in the sign or other industries, particularly in the United States, but it's gaining ground and becoming more widely available as a coating option. However, because it's not as widely used as liquid coating, color palettes for powder coating are generally more limited than those of paints, but custom colors can be developed. Powder coats can also be metallic or clear and can range from high to low gloss. Additionally, powder coat textures can range from smooth to wrinkled to rough, and since powder coating doesn't involve use of VOC solvents, it's considered a more sustainable coating process than painting. Few sign fabricators have in-house powder coating equipment, so most powder coating is subcontracted to outside suppliers. Porcelain enamel. Porcelain enamel is an extremely durable coating in which finely ground glass particles are applied to a metal base, typically aluminum or steel in the sign industry, and heated to a very high temperature to fuse the particles into a smooth glass coating, which is noticeably thicker and richer than most other coatings used in the sign industry. Porcelain enameling has ancient roots in both Eastern and Western cultures, as can be seen on jewelry and other decorative objects such as intricate Chinese cloisonne vases and lavish French Fabergé eggs. In signs with porcelain enamel coatings, the graphics are typically fused into the coating, rather than being applied later by a different process, resulting in very durable, surface-integrated graphics. For this reason, porcelain enamel is an ideal coating for signs in high-wear environments, such as subway stations and exterior exhibits. In fact, the porcelain enamel signs of the London Underground are so emblematic of that system that miniature enameled signs are sold as souvenirs of London. Recent developments in signage application of porcelain enameling allow graphics with an improved degree of resolution and tonal range, as well as wider color ranges. Although exact color matching isn't always possible, porcelain enamel coatings can range from transparent to opaque, but opaque colors are typically used for signage. The gloss level of porcelain coatings can range from high to low. Porcelain enamel coatings are generally used on flat sign panels, as these coatings don't readily conform to complex three-dimensional shapes. Few sign fabricators have porcelain enamel equipment, so most porcelain work is subcontracted to specialty suppliers. A porcelain enamel sign is shown in figure 5.68 of chapter 5. Patinas and oxide coatings. Patinas and oxide coatings occur only on metals and are the result of corrosion, a chemical reaction between metals and elements, such as oxygen or sulfur in the environment. The term patina refers to the coatings that form on the yellow and red metals, such as bronze, brass, and copper. When exposed to weather, these metals will naturally turn brown and then greenish, just as a copper penny does over time. This process can be hastened and the resulting colors somewhat controlled by the application of different chemicals to the copper alloy metals and then sealing the surface to prevent further oxidation. See figure 6.65. Verdigris, a green or greenish-blue coating, such as that on the Statue of Liberty, is a common patina, as is a dark brown patina. Anodizing is a process by which the oxide layer that naturally forms on the surface of aluminum is thickened by an electrochemical process, forming a very hard, integral, almost glass-like surface coating. The resulting aluminum oxide coating is effectively clear, although slightly cloudy, making clear anodized aluminum slightly less shiny than unanodized aluminum. Anodized aluminum can be colored in bright or subtle tones using various dyes and relatively new processes allowing full-color photographic quality images to be integral to a clear anodizing coating. Aluminum sheet can be anodized by the sheet manufacturer, or aluminum components can be anodized on a batch basis after assembly. Most sign fabricators don't have anodizing facilities, so they either use pre-anodized sheets or send aluminum sign components to an outside anodizing supplier. Rust is an oxide layer that develops on the surface of all iron and steel, except for stainless steel. Unlike the aluminum oxide coating that strengthens the surface of anodized aluminum, the iron oxide or rust that forms on steel typically weakens it and detracts from its appearance. For this reason, steel used in signage is almost always painted to prevent rust. That said, an iron oxide coating can lend a certain rustic appearance, and Corten and other weathering steels are specifically manufactured to oxidize to a reddish brown naturally over time in exterior environments without losing their strength and without extensive surface flaking. All patinas and oxide coatings conform to complex shapes, particularly if applied under controlled versus natural conditions. Gloss levels vary with the base material, process, and any additional top coating used over the oxidized coating. Plastic and vinyl films. Plastic and vinyl films are thin, flexible, self-adhesive sheets that can be applied to a range of sign materials. There are clear protective films, including anti-graffiti films, that are applied to materials with or without other coatings, as well as translucent and opaque films in a fairly limited range of integral colors. Other plastic films stimulate metal, wood, and stone surfaces with varying degrees of success. Some are very realistic, others aren't. High resolutions and unlimited colors and tonal ranges are available when white vinyl films are digitally imaged with graphics. Several examples of signs with plastic and vinyl film firms are pictured throughout this book. Vinyl and plastic films with a high gloss level are widely available, and some films have semi-gloss or matte surfaces. The self-adhesive films used in signage are suitable for application to primarily flat surfaces, as they typically don't conform to complex shapes. Although stretchable, films have been developed to wrap objects with complex curves, such as automobile bodies and train car interiors. Finishes. In an effort to reduce the confusion between the terms, finishings and coatings as used in this book, the term finishes refers to textures created directly on the surface of certain sign materials. Finished textures can be imparted to the material surface either during the material manufacturing process or after manufacturing. Typically in the sign fabricator's shop after the sign material has been worked or assembled by the shop personnel. Most post-manufacturing imparted finishes are created by mechanical devices using abrasives such as belt sanders and sandblasting guns, although some are created by chemical etching. The texture of mechanical finishes varies with the texture of the abrasive used. The smaller the abrasive particles, the smoother the finish, and vice versa. Although there is a wide range of both manufacturing imparted and post-manufacturing imparted finishes, this section will focus on the basic finishes for most of the essential sign materials. Metal finishes. Metal finishes can range from a completely smooth, mirror-like polish to coarser textures consisting of scratches to the metal surface. One of the most common examples of the latter is a grained, directionally texture, often called a brushed or satin finish. Another type of scratched finish is a non-directional or random finish, in which the scratches have no discernible grain direction. See Figure 6.66. Other mechanical finishes for metals include sandblasting and bead blasting, which produce a uniform blanket of pits rather than scratches in the metal surface. giving the surface a more frosted look than scratched finishes. Metal surfaces are also sometimes acid etched, which creates a finely frosted surface. Some metals are available with unique manufacturing imparted finishes, such as embossed textures, but in the sign industry, most metal finishes are imparted in the sign fabricator's shop. See figures 6.67 through 6.69. Plastic finishes. Plastic finishes are typically imparted in the manufacturing process and are rarely altered in the sign fabricator's shop. The most common factory imparted finish for acrylic and polycarbonate sheet is a completely smooth mirror-like polish. Although some frosted and other textured finishes are available for these commonly used sign plastics, other plastics used in the sign industry have factory-imparted finishes that range from completely mirror-like smooth to pebbled to directionally grained. Glass finishes. Glass finishes can be imparted by the glass manufacturer or glass supplier. See figure 6.70. The most common is the typical completed smooth polish. A wide range of glass surface textures and patterns can be created in the manufacturing process, while others are imparted by mechanical or chemical processes after manufacturing. Chemical etching and sandblasting are used to create frosted glass finishes, with chemical etching producing a finer frosted texture than sandblasting. Note that there are some considerations in applying frosted finishes to tempered glass. Mechanically produced scratch finishes are not typical for glass. Stone finishes. Stone finishes are typically created by the stone quarry or stone supplier. Stone finishes range from completely smooth, mirror-like polishes to rough-hewn textures. Honed stone finishes are produced mechanically and are smooth but non-reflective, effectively similar to a frosted finish on glass or metal. Thermal stone finishes are more roughly textured, created by heating the stone surface, causing it to break along the crystalline structures inherent to certain granular stones such as granite. Cleft finishes are also rough textured, imparted along the natural layers inherent to certain sedimentary stones such as slate. See figure 6.71. Chapter Wrap-Up. This chapter has explored the many facets of designing the three-dimensional hardware objects of a sign program. This examination included development of sign shape or form, mounting and size, as well as an overview of the basic lighting techniques, materials, coatings, and finishes the EG designer manipulates in the design of a sign program's hardware system. A basic overview of digital display units has also been included. The hardware system, because it is a three-dimensional embodiment of signage, is often considered the most complex design challenge, but it is that inherent complexity that also makes it the richest for creative manipulation. The hardware system is where signs come to life as physical objects in the built environment. And this chapter has provided the EG designer with a sampling of the basic tips and tools for creating those objects. There's a whole world of forms, materials, processes, and techniques for the EG designer to exploit in developing a sign program's hardware system. We encourage you to tap into it.